Okay, so some of the next things that we're going to talk about are the properties of elements and ions that we can use the periodic table to predict, or periodic trends. The first one we're going to talk about is atomic radius. Now this is often just the radius of an atom, but oftentimes it's measured by the distance between two atoms in a molecule, or the covalent radius. If you can tell how far the nucleus is, the nuclei are from each other, and divide by 2, you'll get a good approximation of the radius of an individual atom. Now here what we have is a plot of radius as a function of atomic number. And so what we're going to try to do is we're going to look for the periodic trends. What happens as we go across a period of the periodic table? And what happens when we go up or down a group or family, a column of the periodic table? Okay? And so here we have a few groups pictured. We have the noble gases in red down here, and of course the alkali metals in blue up here. Now, so let's take a look at that as a function of group or family. As we go down a group from lithium to sodium to potassium to rubidium to cesium, what's happening to our radius? Well, of course, it's increasing. The radius is going up as a function of going down a group. Okay? The same thing holds true for the noble gases. Atomic radius increases as we go down a group. And so that is the periodic trend. As you go down a group, atomic radius increases. Okay? What happens when we go across a period? So what we're going to do is we're going to go from the left side of the periodic table, from lithium, group 1, all the way to group 18 or 8A, and to neon. And you can see that what happens? Well, the radius goes down. As we go from left to right of the periodic table, the atomic radius for elements decreases. And we can look at any period, any family, those two trends hold true. Okay, so now that's the trend, half the battle. We also want to figure out why that is the case. Now, we look at the plot in a little bit different method. We can see that as as we go down the group, we can see that the radius increases, and as we go left to right, the radius decreases. All the numbers you see values are radius in picometers. So lithium has a radius of 152 picometers, but as you go down to potassium, 227. Lithium, again, 152. When you go all the way over to neon, we're down to 70 picometers. Okay, so what is changing as we go down a periodic, down the periodic table, or down a group or column? Okay, of course we are increasing the number of protons and we're increasing the number of electrons. Also, we're putting electrons into higher and higher n values, energy levels. And we know that gives us information about the size of the electron clouds. So the higher energy the electron has, the further away it is from the nucleus. So that's very intuitive. You add throw on more electrons into higher energy levels, they're going to get further away from the nucleus, and hence larger atomic sizes. But what is the difference between lithium and neon? Neon has more protons, more electrons than lithium, but its radius is actually decreasing. Okay? To figure out why that's occurring, we have to go back to the idea of shielding, and a new term that we're going to utilize called the effective nuclear charge. Remember that the electrons, if we take a look at lithium, the electrons in the 1s orbitals are flying around here, very high rates of velocity, and what they do is they shield or block some of that charge that the 2s one, the valence electron of lithium, observes. Okay, so what you can do is you can do a quick measure of the effective nuclear charge for valence electrons, or what they observe, and that is the number of protons minus the number of core electrons. Okay, lithium has 2 core electrons, 3 protons. 3 minus 2 is +1. Those valence electrons, or the valence electron for lithium, observes a +1 nuclear charge effectively. Okay, if you do that same calculation for other elements in the rows, okay, we already know lithium has the effective nuclear charge of +1, an effective nuclear charge, or ENC as we'll call it, is again number of protons minus the core electrons. It turns out that as you go left to right, we're increasing the number of protons, but the number of core electrons, of 1s2 core electrons, is going to stay the same for that period, and then again for all other periods. So you can calculate the effective nuclear charge for carbon, and it turns out to be +4. If you do it for nitrogen, that turns out to be +5. And then fluorine +7. Neon turns out to be +8. So you're adding electron, or excuse me, you're adding a proton. You keep this the same. So your effective nuclear charge steadily increases as you go left to right. Okay, so what does that do? That effective nuclear charge is a stronger attraction for those valence electrons, and that pulls them in, attracts them to a lower and smaller radius. And that's why as we go left to right, the effective nuclear charge increases, pulling in the electrons, decreasing the radius. It turns out that the effective nuclear charge for going down the row is actually the same. So by adding more electrons with the same effective nuclear charge, really doesn't attract them any greater, and because they're higher energy away from the nucleus, it just increases the radius. Okay, so here we can see the trend for atomic ions, or excuse me, atoms and their cations. So here we have pictured lithium atom with a 152 picometer radius, and the lithium ion with a much smaller 60 picometer radius. And it turns out that if you lose the valence electrons, the electrons on the outer edge of the atom, you're going to decrease the ratio, or decrease the radius, excuse me. So it's very intuitive that cations are going to be smaller than their respective ions, or excuse me, respective atoms, because you're losing electron. Your electron that you're losing is the outermost electron, the furthest away from the nucleus. Taking that away decreases the radius. Okay, so you'll see that time and time again. The ion, the cation, is much smaller than the neutral atom. Okay, the same periodic trend holds true as you go down a column. The atomic radius increases. As you go left to right, the atomic radius decreases. Okay, for atoms that can lose more than one electron, or multiple versions of electrons, such as iron or transition metal, you're going to have +3 or +2. If you think about what's happening, we can figure out which ion will be smaller. Okay, the iron +2 ion effectively says that it's lost 2 electrons. Iron +3 has lost 3 electrons, so iron +3 will have the smaller radius. It's lost more electrons. Also, the increased nuclear charge, the increased positive charge, is also going to work to pull in electrons a little bit more effectively. On the other side of the coin, we have their anions. And what are anions? They've gained electrons. You're throwing electrons into higher energy levels, or the highest energy level, the outer electron shell. There's going to be a little bit more repulsion. Same effective nuclear charge, so it's not that big surprise that we see that anions are bigger than their neutral atom counterparts. And that's going to be true. And again, the same trend holds true. As you go down a family, the ions and atoms increase in size. As you go left to right on a period, the ions and atoms decrease in size.